Today's lesson is on two periodic trends, and these two items are ionization energy and electronegativity. Next unit is going to be on bonding, and we're going to look at the reactivity of various elements, and this is going to involve the electrons. So why does it involve the electrons? Because when two atoms interact, it's the outermost part of the atoms that combine with each other, and that's where the electron clouds are. Now, typically, atoms can lose electrons, and this is going to be based on something called ionization energy, or atoms can gain and share electrons, and this is based on the atom's electronegativities. So, you may be asking, what is ionization energy and what is electronegativity? Well, ionization energy is something that you could probably figure out just from the word itself. So an ionization energy is the energy needed to ionize something. Specifically, it's the energy needed to remove the outermost electron. And this energy is based on something called Coulomb's law, which you might have had in physics. And it's this equation right here. And let's talk about this equation and how it relates to the atom. So the F stands for the force, or the energy needed to remove the electron, and that is based on this, which is just a constant, times Q1 Q2 over R squared. So what is Q1? Q1 is the effective nuclear charge, which we talked about in the last lesson, and this can change depending on the element involved. Q2 is the charge of the outermost electron, and that's the same for all atoms. Electrons have the same charge. K is a constant, as I mentioned, and R squared is the atomic radius squared. So these are the factors that are going to be important when we figure out how much energy is needed to remove the outermost electron. And I'm going to give you a little bit of an analogy because you actually have probably a basic feel for this equation. Let's take two magnets, and let's talk about the attractive forces between two magnets. It's going to be based on a couple things. One, how strong the individual magnets are. That would be related to the Q values we were talking about. So the stronger the magnets, the stronger the attraction. It is also going to be based on how far apart the magnets are from each other. Are they close or are they far apart? So if you want a really strong attraction, or if there's a really strong force between the magnets, you would have very large magnets or very strong magnets that are very close together. And they're harder to pull apart or harder to remove from each other if they're strong and close together. They're easy to remove from each other if they're weak magnets that are far apart already. So this is the same thing with removing electrons from an atom, where you're removing it from the attractive forces of the nucleus. So the greater ionization energy is the greater the force, which means it's harder to ionize and it's harder to lose an electron. So how do I get a big ionization energy? Well, that happens when you have two things going on. You have both a large effective nuclear charge, so this Q value, which is on the top of the equation, that's a big number. And you also have it when the atom is very small, where the radius is small, and that's because the bottom of the fraction is a small number. So the force is big when the numerator is big and the denominator is small. So when the effective nuclear charge is big and the radius of the atom is small. So I kind of just pictured this kind of as a way to see this would be weak, because it has a big atom with a small effective nuclear charge, and this kind of is representing a small atom with a large effective nuclear charge. So let's recap from our previous video on effective nuclear charge. And if you remember, or if not, you can take out your notes, hopefully you have this. As we went across the periodic table from left to right, the effective nuclear charge increased. And that's because as you went across the periodic table, each atom had one more proton than the atom before. So the nuclear charge was increasing. It, however, decreased significantly when you started a new row. Why was that? Because when you started a new row, you ended up with electrons between the outer electrons and the nucleus, and we call that shielding, or it is blocking the effect of the nucleus attracting the outer electrons, because the nucleus is attracting at the same time the inner electrons are repelling the outer electrons. So as you go across this way, it increases because you add more protons, but not much more shielding. And then it drops when you start a new row because you have a lot of electrons in between the outer ones and the nucleus. And it increases as you go this way, and then it decreases when you start a new row. There is a slight increase as you go down the periodic table, but not much. What about the atomic radius? Where is the atomic radius small? So here is a picture, remember from WebElements. You can go to WebElements.com and pull this up. And as we went across the periodic table from left to right, the atoms got smaller and smaller. But when you went down the periodic table, the atoms got bigger and bigger. So here again, to summarize that, the atomic size decreases as we go from left to right, but increases as we go down the periodic table. So if I want a large force or a high ionization energy, that would occur when I have very small atoms and large effective nuclear charges. So where do I have small atoms and large nuclear charges? Up in this right-hand corner. So ionization increases as you go this way, and ionization decreases as you go this way. So you might say, but Miss Backus, the effective nuclear charge increased as you went this way. So wouldn't that make the ionization energy increased when we went down? Well, no, because the radius changed dramatically. And remember that equation? We squared the effect of the radius. It's r squared. So the atoms were getting bigger and bigger, so that r squared value was getting bigger and bigger. And so the ionization energy decreases as we go down. So this is the trend. Ionization energy increases this way, but decreases this way. So what about electronegativity? Well, electronegativity is defined as an atom's ability to attract electrons when bonding. So now I want a strong force once again, which is also based on Coulomb's law. So I need a large attraction. And how do I get that large force? I need a large effective nuclear force, and I need a small atom. That sounds very familiar. Well, let's see if you can do this. So I want you in a second to pause the video, and yes, I actually mean for you to pause the video and predict the trend. Going from left to right, does electronegativity increase or does it decrease? And going down the periodic table, does electronegativity increase and decrease or decrease? Now remember, it says electronegativity is an atom's ability to attract an electron. So how can I attract electron? I have to have a strong effective nuclear charge, and I have to have a small atom, because then the nucleus has a then the nucleus has a very large attraction for any outer electrons, and it's the outer electrons that will be the area where the bonding is going to occur. So go ahead, pause the video, and be decisive. Left to right, does it increase or decrease? Top to bottom, increase or decrease? So did you get it right? Well, it's the same trend as the ionization energy. It increases because the force increases as you go from left to right, and decreases as you go top to bottom. So hopefully you got that right. If not, write that down. Maybe rewatch this a little, see if you could figure out why you got it wrong. So here's a table of electronegativity values. which is in your appendix of your problem book. And I want you to look carefully at this table because something seems odd. So see if you can find something very odd about this table. Can you find it? We said things increase this way and decrease this way. Can you find something that's odd? Well, hopefully you did, and that's right here. What happened here? Why are these values all 0? We were supposed to increase as we went from left to right, which we did, but then the noble gases had 0 values. So it increased going from left to right, except for the noble gases, and decreased going top to bottom, except for the noble gases. So why don't the noble gases have an electronegativity value? Well, you might have learned this from the NOVA video, is that the noble gases have a full outer shell. So when we talk about bonding and gaining electrons, there is no place for these new electrons to go. The shells are already full. So to add an electron to a noble gas, there's no room. Where would this electron have to go? In a brand new energy level. And that brand new energy level would be farther away, a large R, and it would also have a whole bunch of shielding electrons. So a very small Q and a very large R. So bonding doesn't usually occur with noble gases. And it's a little more complicated than that, but we'll talk about that more in detail later. So hopefully you got the trends. Ionization and electronegativity follow the same pattern. They both increase left to right, and they both decrease top to bottom because they both involve the force that is due to the effective nuclear charge and the size of the atom. So, hope you got it, and thanks for listening.